Hey you guys, this is the introduction to the next unit. Um, Here's your FLT, okay? So go ahead and write that down. We'll talk a little bit about what this unit is, and we'll go from there. Okay, so given a non-polynomial function, I will create a polynomial lookalike function by process of overlapping and analyzing error. Okay, so remember back in Calc AB, so just a quick reminder, Calc AB composed of three big ideas. There was limits, which led to derivatives, which led to the antiderivative we call integrals. Okay, now BC has those three elements, okay? And then they sprinkle in some BC concepts. So we're still going to revisit limits, derivatives, and integrals with the BC lens. But there's a fourth big idea, a huge one. Big idea number 4, which is series. And you guys are learning this now. We have an advantage because, most BC courses, they will teach you AB and BC all smushed together in 1 year. So time is definitely on our side here, okay? Most people tend to struggle with series, not because it's difficult, but because it's the last thing on the menu, okay? So if you guys think about any a school where they would teach AB and BC all in 1 year, when they get closer and closer to the AB exam, usually what happens is series gets cut, and that's why those students tend to not do well on the BC exam, okay? But you guys have an advantage. Again, you have a lot of time on your hands, so we'll take our time and we'll learn it very well. We're going to spend maybe about 5 to 6 weeks on this, whereas maybe in a ABBC course smush into 1 year, they will learn it maybe in 1 or 2 weeks, okay? It's a very new concept. It takes some getting used to, but by the end of it, you will feel very confident, okay? Okay, so here we go. Just a little bit of a review before I jump into Desmos with you, okay? Recall back in pre-cal or integrated math 3, okay? And it's okay if you forgot. Even functions, and sorry, I should say functions with even degrees, and then functions with odd degrees all behave the same way. So if you ever forget, you could always think about the two most common ones. So the most popular even degree is x squared because it has a even degree. So x squared, you guys know, is a parabola. Okay. So anything with the even degree is going to behave the same way. All right. Notice if I did like negative x squared, you guys know that that's just a reflection. But notice how they both point in the same direction. So whether you go towards the left or to the right here, they both go up towards infinity or they both go towards negative infinity. So they both go in the same direction, okay? So something like x to the fourth, you don't know exactly what happens in between, but you know that they're going to both point in the upwards direction. I did the dotted lines because we don't necessarily know what happens in between, but by behavior, we know that x to the fourth will both point up in the same direction. Now, if it was a negative x to the fourth, then you know they would be pointing both down in the same direction. Okay? So, same with x to the 10th, okay? We don't necessarily know what happens in between, but we know that they both point upwards if the leading coefficient is a positive, okay? Same thing with odd degrees. The most popular odd degree is x. Y equals x is just a line. Now notice, as you walk towards the left here, and I'll use purple, if you walk towards the left, you know it's going all the way down to negative infinity. But if you walk towards the right, it goes all the way up to positive infinity. So they go in different directions. So over here, it's the same for even degrees. But for odd degrees, it's different directions. Okay? Same idea. Now, if you had negative x, that would just be a reflection. So they would just point in the opposite directions there, okay? So if I ask you guys, what does x to the 7th power look like? You don't know what happens in between, but you know that if you walk towards the right, it'll go all the way up. And if you walk towards the left, it'll go all the way down. We don't necessarily know what happens in between, but we know that that's the end behavior, okay? Same thing here. If I gave you negative x to the 11th, you know that it'll start to the left going up, and downwards, it'll go to the right. Or to the right, it'll go downwards. Okay, so that's just a little bit of a quick review. I'll show you how we use that in a second. Okay, on to Desmos here. All right. Take a look at this. Take a look at this picture, okay? Tell me what that function is. All right, pause and press play whenever you're ready. Okay, most of you will say that it's a linear function. That's y equals x, right? Okay, but here's the thing. How do we know for sure? Right? So obviously it looks like a line, but what I'll do here is maybe I'll zoom out a little bit. Okay, is it still linear? Okay, it still looks linear, right? But if I keep going, you notice that line starts to bend a little near the end. This is actually a sine function. Fooled ya. Okay, so here's the thing. We're trying to create a polynomial lookalike function for non-polynomial functions. So in this case, we're going to try to come up with a brand new function that will mimic the sine function. Okay? So in essence, you're coming up with like a doppelganger. You're coming up with a twin that'll make it look like the sine function. So here's what we noticed so far. When we zoom in close enough, when we're really close to 0, okay, sine x was very similar or approximately equivalent to y equals x. Okay, so remember, when we zoomed in, sine x looks just like x. Okay? So here's what I'm going to do. Well, how close was it? Right? What I'm going to do here is I'm going to go ahead and graph y equals x. Okay? So obviously the green graph is the linear function. The red graph is the sine function here. Now if I put on some, let's put on some values, okay? Now if you notice, when we're really close to 0, that green right there and that red is overlapping to the point where you can't tell which one's which, right? They're mimicking each other. But do they mimic always, right? So if you notice, when we pass, I'm just going to hold this here, when we pass about x equals about negative 0.5 and further, they tend to split up, right? So they're overlapping, and then they start to go their own separate ways. Okay? So there is an error between the two. The error represents the distance between the two functions. Okay? We call that error. So here's what's happening. We're going to calculate that error. All right? So the way we do that is, if you want to find out how far something is from another, so for instance, if I wanted to just to put simply, if I had a point at 4 and then I had a point at 1 and I want to find out how far 4 was from 1, what would you guys do, right? You would pretty much take one value and subtract it from the other value to find the distance. That's a distance of 3. So what we're going to do here is we're going to subtract the two functions together to calculate our error. So what I'm going to do is I'm going to move this over. All right? So sine x minus x will represent the error. Okay? Remember, the error is just the distance in between them. All right? So I'm going to type this out here. I'm going to go ahead and graph my error. Y equals sine x minus x, and I'll do that in black. Okay, so look, just so you guys understand the graph. When we were really close to 0, the green and the red functions overlap. That's why the black function is at 0, because that represents the distance. Now, as we go further and further apart, there's a little bit of distance right there if you look at my cursor, which is why there's a little bit of distance right there with the black function. And the further out I go, the distance gets larger, which is why that curve goes further away from the x-axis. Okay, make sure you guys understand that before we move on. Okay? Okay, so here's the thing. If I can fix this error, I can make my doppelganger, I can make my polynomial lookalike, my twin, a little bit better. Okay? So take a look at just the black function. Remember, this is our error. Okay? Let's try to mimic our error here. Okay? So if you guys take a look at this graph, what does it closely resemble? Does it resemble an odd degree function or an even degree function? Okay, pause and press play whenever you're ready. Okay, this closely resembles an odd degree function because we know it starts in one direction. So if we walk all the way to the left, it goes all the way up. But if we walk all the way to the right, it goes all the way down. So it's starting and ending in different directions. So we know it's going to be an odd degree. Okay, so it looks really close like a cubic function, but flipped. Okay, because look, if I type in x to the third, it doesn't look like that black function, but the moment I slap on a negative, it'll flip, right? So it's similar, but can we make it look a little bit more like that one? So it looks like it's a little bit more compressed, squished. Do you guys remember how to squish a graph? Okay? How to dilate a graph. So, pause and play whenever you're ready. It deals with putting in some type of coefficient in the front. So let's say I put in the number 2. Did I make it look more or less like that graph? Okay. Notice how when I put in 2, it doesn't get wider. It actually gets a little bit more narrow. So if I put 4, 5, or 6, it just gets even more narrow. So the only way to fix that is what we're going to do is instead of multiplying it by it, we're going to divide by a value here. So let's try the number 2. Okay. Gets a little bit wider. So let's do 3. Closer. 4. 5. And the magic number here is 6. All right. Now, it's not going to match perfectly, but notice how we're pretty close to it when we're close to 0. All right. So look, back onto our notes here. Our error, we were able to come up with a polynomial lookalike for our error. So our error represented negative x to the third over x to the sixth. Now, that closely resembled our error, sine x minus x. Now, did it match exactly, right? Was it a direct overlap? Only when we're close to 0, but if you notice in the graph here, if we go further out, they'd start to separate, right? So what I'm going to do here is that's actually an approximation still. All right, so here's what we're going to do now. We're going to see what happens if we were to isolate isolate sine x. So what I'm going to do here is I'm going to go ahead and add x over here. All right, so now here's what we've done. Sine x is now approximately that positive x minus, why did I write x to the sixth there? Minus x cubed over 6. So here's what we've done, all right? We've now improved how our polynomial lookalike will look like with our sine function. So let me go ahead and erase this real quick. Okay, so here we go. This was our original sine function that we're trying to mimic, okay? So originally we had x, okay? So let's go back here real quick before I graph the second one. When we used x, it looks like it overlaps at the x value of about maybe negative 0.4 all the way to about positive 0.4. So I'll just make a note here that it overlaps maybe about from negative 0.4 to positive 0.4. Okay? So now what we're going to do is let's graph our new polynomial lookalike, which is x minus x to the third all over 6. Okay? So let me zoom out a little bit. Does that look better as a polynomial lookalike than that linear function that we had, right? Hopefully your answer is yes. So here, this black function, actually I'll keep it as green just to keep the same pattern. This polynomial lookalike, if you notice, it overlaps that sine function a lot better than that linear function because it actually curves with it. So it's starting to behave just like it, right? But if I zoom out a little bit, does it behave exactly like the sine function? Absolutely not, right? So at some point it starts to separate. So my question to you guys is, from where to where does it overlap, right? So it starts to overlap, or actually starts to separate at about negative 0.1, right? And positive 0.1. But right after 1, that red and green graph starts to separate. It starts to show a lot of error. But from negative 1 to 1, now we have an overlap. That's strange. Let's try this again. Now we have an overlap. Oh no, it's freezing. There we go. Now it's starting to overlap at about negative 1 to 1 now. So we've increased our overlap, meaning that we have a better polynomial lookalike. All right? Now, in the back of your mind, you're probably asking, what the heck is this all about? Like, who cares if it overlaps? I will tell you the point of that story, okay? So just hang on to that. So look, this right here is just an approximation, because right after 1 and right before negative 1, they start to separate, right? So what we can do here is just like the linear function, we can calculate our error. So what we're going to do here is we're going to take all this and we're going to subtract it over to the other side. So on the left, I'm going to have sine x minus x cubed over 6. Now you can move over the terms separately if you wanted to. It doesn't change anything. So context. Remember, what does it mean when we're subtracting the two functions? Okay? Pause and play when you're ready. Just like this here, when we're subtracting the two functions, we're finding the error, right? So here, this is our error. And remember what error means? It's just the distance, okay? The distance between the two functions. So here we go. I'll graph it for you guys. So this is going to be sine x minus the quantity of x minus x to the third all over 6. Okay, and I'll use black just to keep the same pattern. The black function here is our error. The red function is our original sine function, and the green function was our polynomial lookalike, our doppelganger, our twin, okay? So, just so that we're not all confused, if not already, we'll just look at the black function here. That black function kind of behaves like an odd or an even degree function, okay? Pause and play when you're ready. That looks a lot like an odd degree function because they end in different directions. It's starting at the bottom and then it ends at the top, right? So we know it's going to be some odd degree. But the thing is, we've already used x cubed and we know this is not linear. So what's the next best thing, right? Pause and play when you have an answer. So some of you may be thinking that this looks a lot like x to the 5th. Okay, now does that look like that black function? Sort of, but not really. It's pointing in the same direction, but it's not as wide as it should be, right? Do I have to put a negative in the front? Okay, this time I don't put a negative in the front because then it's going in opposite directions, so it has to stay positive. So how do we make it wider in a sense? We would have to put some type of coefficient in the front. Now, do we put in a whole number or do we put in a fraction, right? So notice how when we put in whole numbers, it just gets more narrow. So what we want to do is we want to divide by something. So we start to guess. Let's start at 2, okay? Maybe we could do a little bit better than that. So we keep playing with this. I'm just going to increase the number until it starts to look like it. Where do you think it'll start to look like that black function, right? So the answer here is, hang on. Let's try 40. Let's try 50. So you notice how here I'm trying to get it as close as possible. The magic number here is actually 120. Okay? Now remember, we're only focusing when we're really close to 0. Okay? So obviously there's going to be some error here too. All right? Now, why is it 120? I'll talk about later. All right? There is a process to that. All right? I didn't just make up a number. So here's what we've uncovered. The error looks a lot like x to the 5th over 120. Okay, so the error, that black function, okay, can mimic what we have over here. So here's what I'm going to do now. What I'm doing here is I'm looking at the overlap and then I'm analyzing the error. Okay, and once I can find out what the error is, I could slowly improve my function from the beginning. Remember, I started off with just x right here. And then I improved it to x minus x cubed. And what I'm doing is I'm trying to make it better and better so that it starts to mimic the sine function more and more and more and more. Okay? So here's what I'm going to do. I'm going to go ahead and I'm going to bring this quantity back over here. Okay, so that'll cancel out. I'm going to bring over x minus x cubed over 6. So now what I have on the left side is sine x, and that is approximately equal to x minus the x cubed over the 6 plus x to the 5th over 120. Okay? We're going to do this one more time, all right? Just so that it really sticks. So if you're not really fully grasping what's going on, don't worry. I'm going to recap everything here, okay? So here's what I'm going to do. I'm going to go ahead and graph the new polynomial lookalike, which is x minus x cubed over 6 plus x to the 5th all over 120. That red function right there is your sine function, what we started with. That green function right there is what we started with at the very beginning to try to mimic the sine function, and then we slowly improved. And then here's our new polynomial lookalike. Okay, notice how it starts to hug the sine function even more. Okay, so same question to you guys is, where does it overlap? Okay, so roughly from where to where does it overlap, right? It's looking like, I hope you guys agree with me, it starts to overlap at about a little bit before -2, and then it starts to separate right there. Starts to separate a little bit, right? So a little bit before -2, but I'll just put -2 all the way to about +2. Again, these are just approximations, but notice how the overlap has gotten better each time I added a new term to it, right? Okay, now same question to you guys. Is the green function an exact duplicate of the red function? So the answer is, well, yes and no. Yes, because it overlaps, but only up to a certain point, right? But if you look at the whole picture, if I zoom out a little bit, definitely this green function is not a doppelganger of this red function, okay? So eventually, once you pass 2 and -2, there's an error, right? There's a distance between the two. So we're going to go ahead and calculate error one more time. And how do we do that? We take this entire quantity and we subtract it over to the other side. Okay, so here's what we have. Our error is going to be sine x minus all that. So x minus x cubed over 6 plus x to the 5th over 120. I'm not going to distribute that just because it'll make things a little bit easier here. So before I move on again, what does error mean? Pause and play when you're ready. Remember, error is just the distance between the two functions. Okay? So I'm going to go ahead and graph the error here. Sine x minus the quantity. I'll copy paste this guy right here. Okay, so make sure you guys understand this graph. So we said that there was an overlap from -2 to 2 with your red and green function. So take a look. When you had an overlap with your red and green function from -2 to 2, their distance is relatively 0, which is why the black graph is at 0 here. And the moment these two start to separate, there starts to be a distance between the two. Okay? So here's what can happen. If we can mimic what that error is, we can improve our error. So let's get rid of everything else except the error function. What does that look like to you guys? Okay? If we can mimic what that error looks like, is it an odd degree function or an even degree function? Pause and play when you're ready. That looks a lot like an odd degree function because they start and end in different directions. Now, what odd degree function does it look like, right? Well, we already used the linear function. We already used the cubic. We already used the quintic. That's x to the fifth. So what would be an appropriate function to use? Well, that's your next best odd function. So x to the seventh. Okay. Now, is it facing in the same direction? Okay. Hopefully your answer is no. It's kind of tough with distance learning because I can't hear you guys. So what do? How do we make it look kind of like that black function? We have to reflect it, right? And how do we reflect it? We got to slap on that negative, right? So at least here, even though it doesn't look like it, at least it's facing in the same direction. Now, how do I make it wider, right? So by now, I think you'd know, or I think you'd agree that we have to divide it by some number. What number is that, right? So is it 10? Is it 100? Is it 200? 300? 400? So here's the thing, like, do we go and guess all day? Or is there a pattern to this, right? So take a look at the denominator values, okay? If you will, I'll put a 1 underneath that x, okay? What is the significance with the numbers 1, 6, and 320? Okay, it's not obvious, okay? But think about that there. If you've taken statistics or are taking statistics, you will see this very often. I don't expect you guys to know it. But 6 here, another way to write 6 is 3 times 2. Actually, no, I'll do 3 times 2 times 1. Okay? 3 times 2 times 1 is 6. Right? So where do you guys think we got 120 from? Pause and play if you see a pattern. We're looking for patterns here, okay? Okay. If you figured it out, great. If not, don't worry about it. 120 is the same thing as 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120. Is there a pattern to this here, right? So what do you think goes down here with x to the 7th? Pause and play when you're ready. Okay, so here, this is really just 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so if we take a look at the graph, it's pretty close. Okay, now here's the thing. Isn't it very inconvenient to writing all the factors all the way down to 1? If only there was a special symbol for that, right? So in statistics, in probability specifically, okay? If you wanted to multiply a number by everything less than 1, all the way down to the number 1, for instance, 3 times 2 times 1, it trickles down, you would use a symbol called a factorial. A factorial looks just like an exclamation point, okay? So I'll write in your notes here, this represents your factorial. Okay, it's a very short way of writing everything times 1 less, times 1 less, times 1 less, all the way down to 1. All right, so for instance, 8 factorial would just be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so 5 times 4 times 3 times 2 times 1, remember originally was 120. We could just write that as 5 factorial. So this right here is really just 7 factorial. That's way faster than writing it all out, right? Okay, so let me clean this up a little bit for you guys. So we have sine x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I'll even put the 1 factorial over there, okay? We came up with a function that looks just like the error. We call that negative x to the 7 over 7 factorial, okay? So here's what we're going to do. We're going to go ahead and bring this quantity back to help improve our polynomial lookalike function. So now sine x is now similar to x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. Okay, here we go. So let's take a look to see what it looks like now. Okay? So here's our original sine function. Okay? Here's what we had at the very beginning. It was a polynomial lookalike, but it wasn't that great because it only overlapped from negative 0.4 to 0.4. And then we slowly improved our lookalike, and we were able to slap on another term, x to the 7th, all over 7 factorial. Okay, let's take a look to see what that looks like. Okay? So I'll get rid of the linear function. Notice how this hugs the sine function even more. Okay? So it overlaps maybe all the way to about negative 3 now. At about negative 3, a little bit before and after, right? So the overlap here is about from negative 3 to 3 now, which is a big improvement from what we had before. Okay, so you're probably tired of this by now, okay? In theory, could I make the polynomial function or the polynomial lookalike even better? Right? Can you guys guess what would go next? Sine x, if we were to improve it by 1 extra term, based on this pattern, x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. Can you guess what would go next? Okay? Look at the pattern, pause there, play whenever you're ready. So, the next term, as you would have guessed it, I'm sure, is going to be a positive x to the 9 over 9 factorial. So we're going to skip all the errors here now, okay? I'm going to go ahead and slap on plus x to the 9 over 9 factorial. And notice how it hugs even more. It actually goes all the way up to about negative 4 to 4 now. A little bit shy, but it's a little bit further. Okay, what do you think the next term is going to be? What is that next term? That's going to be negative x to the 11th over the 11 factorial. So I'm going to go ahead and type this here. Minus x to the 11 over 11 factorial. Now it hugs at maybe about negative 4.5 now. So notice how the more terms I add, the further it overlaps. I'll say that one more time, okay? The more terms I add, the further it overlaps. Okay? So look, in theory, how much can I overlap? Think about that there. In theory, how much can I overlap? So, in theory, you can go on forever, right? To an infinite amount of terms. We call that a series. Okay? So the term series here, we can go as far as we want. Now I'll just go dot, 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 dot. We can go as far as we want, but we know that the general term, there's a pattern to it. So here's what you guys do. This right here will be your general term. So your general term is basically your pattern. All right? So we noticed a few things. So we noticed that the factorials match up with the degrees, right? So we noticed that whatever the degree is, the factorial is the same thing, right? We also noticed that it alternates in sign. Okay, so how do we mimic that? So what you're going to do here is, to make it alternate, you're multiplying it by a -1. That's what makes it alternate, okay? But you're going to do it to the nth power. N represents the number of terms, okay? We know there's always going to be a base of x to the something, okay? Now, to make things odd, okay, it's going to be 2n minus 1 or 2n plus 1, depending on how you look at it, okay? And I'll explain why I'm doing this here. So down below is going to be the same 2n minus 1, the same power, but factorial. Notice how the factorial is outside of the parentheses there, okay? Okay, so let's see if this works, and let's see if we have to tweak it a little bit. If you only had one term, that means that n is 1. So let's plug in what happens when n is 1 here, okay? When n is 1, I'm going to have -1 to the first power, x to the 2 times 1 minus 1 all over 2 times 1 minus 1 factorial. If I clean this up here, I'm going to get x to the first power all over 1 factorial, but -1 to the first power is negative. This is not my first term. So I got to tweak that a little bit. So what I'm going to do is I'm just going to go ahead and put -1 there. You could do a -1 or a +1. I'll show you both ways, okay? So if we were to just focus on that -1, it doesn't matter if it's -1 or +1 here. I'll show you in a second. If n is 1, okay, that's -1 to the 1 minus 1, -1 to the 1 plus 1. That's -1 to the 0 power, which is just 1. -1 to the second power, which is just 1 there. But more importantly, it's positive. Okay, so this is starting to work. Let's check the second term just to make sure that it works, okay? Now, what if n is 2, right? That's our second term. So let's take a look to see if our formula works here. So that's -1 to the 2 minus 1, x to the 2 times 2 minus 1 all over 2 times 2 minus 1 quantity factorial. Okay, so 2 minus 1 here is 1. So -1 to the first power is going to give me a negative, which is what I want there. 2 times 2 is 4 minus the 1, which is 3. So that's just x to the third. And down below, 2 times 2 minus 1 is just 3 factorial, which is exactly what I have in the second term here. So notice how this general term will spit out every single term that I want. This is our pattern. It all looks crazy at first, you guys, but don't worry, it'll sink in, okay? Okay, so here's the thing. If I eventually stop, okay, if I only put 100 terms, okay, let's say I went out all the way to the 100th term, okay? Would it be an approximation or would it be an exact duplicate of sine x, right? Think about that question. If I go out all the way to 100 terms, okay, would it be an exact duplicate of sine x or would it be an approximation of sine x? It would still be an approximation because it's only going to overlap so much, right? Now, what if you go on forever? What if you go on to the infinite term? Okay, it doesn't stop, right? So what I'm going to do here is pay close attention. Let me copy paste this so that I don't have to write everything again. What if instead I indicate that it goes on forever? Check that out right there. That tells me that it goes on forever. All right? After the general term. If it goes on forever, what happens here is that becomes exactly sine x. Okay? Make sure you guys understand that. If you indicate that you eventually stop, okay, then it's an approximation. If you go on forever with the plus ... it becomes equivalent. Okay, when it goes on forever, we call that a series. All right, so we were able to come up with a polynomial lookalike for a non-polynomial function. In other words, we came up with a twin for sine x. Now, why is this important? Okay, if you guys think about your calculator, right? That sine button. What is so magical about this sine button that it calculates everything for you? Okay? The calculator only knows, it's only programmed to do 4 things. Okay? It knows numbers, and it knows how to add, subtract, multiply, and divide. That's all it knows how to do. Okay? So, the sine button isn't some magical button where if you press SIN, magical things happen. Really, what's happening here is, way back in the day, mathematicians needed to know how to calculate sine. So what they did was they programmed a calculator to spit out this series in an almost instantaneous fashion so that it calculates it on your calculator instantly. So when you guys are pressing the sine of 40, let's say the sine of 45 degrees, what's really happening here is you're typing out 45 degrees over 1 factorial minus 45 degrees cubed over 3 factorial plus 45 degrees to the 5th over 5th factorial. And then it goes on forever, but in a very fast way. And then they spit out a decimal for you. So it's happening within a nanosecond. Okay? So mathematicians were able to come up with a very fast way to explain how sine works. Okay? It's kind of backwards with this big idea here with series. You're kind of learning how things were built beforehand. But what are the implications? And that's something that you guys got to think about. Like, why is it so important to learn about how the sine function was calculated, right? Back in the day when mathematicians came up with an integral, obviously representing real life applications, they came up with an integral that they couldn't integrate, right? So for instance, like, oh gosh, sine of x squared. There is no method right here that'll allow you, like, you can't use U substitution, you can't use partial fractions, integration by parts. None of those approaches work. So what they did was they thought, well, you know what? If I can come up with a polynomial lookalike, I can integrate polynomials very easily because I know the integral of x is just x squared over 2. And I know the integral of x cubed is just x to the 4th over 4. So these mathematicians way back in the day, actually they were physicists, okay? They came up with a way to actually integrate it to come up with a tangible answer. So where does that leave you guys, right? Because you don't want to reinvent the wheel, but think about how that might extend to the other parts of math that you guys may be pursuing in the future. Okay, if you're going into STEM, right? How is this going to be applicable? You might not use series itself, but how can you make something complicated more simple, right? It started way back with the quadratic formula, you know? Someone came up with a way to solve all quadratic functions or quadratic equations. Before that, everyone had no idea how to do it. So this is where the theory and proof comes in, all right, to make things a little bit easier. So this technology right here was pretty much one of the pioneers who advanced technology. Think about it, like before the calculator, BC, right? Calc BC, before calculators, you know, what did people at NASA do, or you know, how did people calculate? Right? Everything was done by hand, but now everything is pretty much advanced through a calculator. So how can we take it one step further? And I'll be honest with you, I don't know the answer to that, but that's something that you want to think about. How can we take it one step further? All right. Okay, I'm talking a lot. Let's move on to the next one. Okay, so we're going to do the same thing, but in a very fast manner with cosine. Okay, here we go. Let's look back on Desmos. I think I blew up Desmos. Okay, there we go. Here's cosine x. When we're really close to 0, what does that look like to you guys? Okay? When I'll zoom in even more. When we're really close to 0, what function does that look like, you guys? Okay, pause and play when you're ready. Okay, cosine x looks a lot like y equals 1. So if you take a look, y equals 1. Notice how there's an overlap there, right? If I zoom out, obviously it's not going to overlap there. It only overlaps maybe at about negative 0.1 to positive 0.1 there, right? So we calculate the error. So we're going to move it over. So that's just going to be cosine x minus 1, which represents our error. Okay, and remember that error represents the distance between the two functions. So I'm going to go ahead and graph the error here, cosine x minus 1. Okay, so take a look. When the red and the black graph were overlapping each other, their distance was 0, which is why the blue graph is at 0 right now. But the moment they start to push away, go in their own directions, the distance increases. Okay, so let's come up with a polynomial lookalike for our error. What does that graph kind of look like there? Okay, notice how they start and end in the same direction. They go from the bottom and then they end at the bottom. That kind of looks like what, right? Pause and play whenever you're ready. That looks a lot like a quadratic function, some type of parabola. So I'm going to go ahead and type in a parabola there. Okay, I'll use a different color. I'll use orange. Okay, now it doesn't look quite like that blue or that purple one there. So what do? We have to reflect it. We'll put on a little negative there. Does it look just like that purple function there? Okay, notice how the purple function is a little bit wider. So what do? We're going to have to divide it by something. Okay, any guesses on what we need to divide it by? All right, think about that. Play when you're ready. I'm going to go ahead and maybe divide it by 2. That's pretty good, okay? So we know that our error is about negative x squared over 2. Okay, I'll bring this down. So cosine x minus 1, that error represents that negative x squared minus 2. Oh, sorry, over 2. So I'm going to go ahead and move that 1 back over. So cosine x is approximately 1 minus x squared over 2. So let me write that out now. So cosine x is now, here's our cosine function. Now instead of 1, I'm going to type out 1 minus x squared over 2. Let's graph it. It looks a lot better than what we started with. Now we're overlapping from about negative 1 to 1, right? Let's run it one more time. So they overlap from negative 1 to 1, but then they start to deviate afterwards. So how do we calculate the error? We're going to go ahead and subtract that quantity over back to the other side. Okay, so now cosine x minus the quantity 1 minus x squared over 2 will be our error. And one more time, remember, error is just the distance between the two functions. So let's graph this and see what happens. Cosine x minus the quantity of all that there. Okay, so notice how here with the black and red graph, when they overlapped, their distance was 0, which is the reason why this purple function is flat at 0 here too. And the moment they start to deviate, that's when the distance starts to increase. Okay? All right. Now, just looking at the error, can we come up with a polynomial lookalike to mimic that? Okay? Is that an even degree or an odd degree function? Hopefully you guys agree that that's definitely an even degree function because they both start and end in the same direction. So we already used a horizontal line. We already used a quadratic function. What's the next best thing? We're going to use x to the 4th. Okay? Now, is it facing in the same direction? It is. So we're not going to flip it because then it will go in the opposite direction. So how do I make it look kind of like that purple function? Pause and play when you have the exact answer here, okay? What do you think goes down here? So some of you may pick it up here. It will probably be 4 factorial. All right. So 4 factorial will represent our error. Okay, now if we know our error, we can improve it. So I'm going to go ahead and bring over this quantity to the other side. So now cosine x will be similar to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And then this is where I'm going to stop, okay? I'll go ahead and graph the last part for you guys. I'm going to go ahead and add on x to the 4th all over 4 factorial. Here's the cosine function. Here's our doppelganger. It starts to overlap even more. How do I improve this, right? If I add more terms, I know I'm going to improve it. I want you guys to think, pause, and guess what that next term is going to be. Press play whenever you're ready. The next term here is going to be minus, not plus, minus x to the 6 all over 6 factorial. Notice how when we add the extra term here, it overlaps even more. What would the next one be? Would it be minus or a plus? It would be a plus. We're alternating in signs. And this is going to be x to the 8th over 8 factorial. Next one is going to be minus x to the 10 over 10 factorial. And I could go all day, right? So here we go. Cosine x is approximately 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And then we have our general term here. Your general term is going to be very similar to what you guys had with the sine function. Okay? Now, we know it's going to alternate, so we know it has to have like negative 1 to the something. Right now, I'll just put n minus 1. Okay, just as a placeholder, okay? Now, x is going to be there. We know all of the degrees have to be even, so you're going to multiply by 2 times n. 2n makes it even, because when you double any number, it's always going to be an even number, all right? And we know the factorials have to match up with the exponent that we have here. So let's pick the third term here. So we know n is 3. So if I plug in 3 for n, let's take a look and see what happens here, okay? So that's going to be negative 1 to the 3 minus 1, x to the 2 times 3, all over 2 times 3 factorial. But this is weird because that's negative 1 squared x to the 6 over 6 factorial. So something's off here, right? So we're supposed to get x to the 4th over 4 factorial. So notice how we got the 4th term, right? Well, kind of. We had x to the 6 over 6 factorial, so we're getting close, but we have to tweak it somehow. Okay, so what are we going to do here? So here's another way. We're going to go ahead and change this to 2 times the quantity of n minus 1. All right, right now you don't need to know why. And down here is going to be the quantity 2 times n minus 1 factorial. Okay, but that still didn't give us a positive value, so we're going to have to change this up here. Let's see. Okay, so 3, oh actually no, 3, if n was 3, that'll work. Let's take a look. Negative 1 to the 3 minus 1. That'll give me a positive, because negative 1 squared is positive. X to the 2 times 3 minus 1. 3 minus 1 is 2. 2 times 2 is 4, so that's x to the 4th power. And then down below, 2 times 3 minus 1. 3 minus 1 is 2. 2 times 2 is 4. 4 factorial, which is exactly what we want. Okay? Now, guessing that general term is probably difficult for some of you, if not most of you, and that's okay. You don't need to know it yet. All right? So here's my question to you guys. Is this expression approximate to cosine or equal to cosine? Pause and play when you have an answer, okay? Since it stopped, meaning since we didn't put a plus dot dot dot, this will always be an approximation. However, if I added on an indication that I go on forever, that becomes an equal sign, okay? AP readers are very picky with you writing good math. I think I explained that a lot last year, okay? So make sure you know when it's approximate and when it's equal. And we'll have more practice once we get into the FRQs there, okay? Okay, so here's what we came up with. We came up with, I'm My son is yelling. We came up with polynomial lookalikes for sine and cosine. Okay? Can we come up with polynomial lookalikes for any non-polynomial function? Can we come up with a polynomial lookalike for e to the x, for the natural log, for square roots? That's something that we'll uncover next, okay? That's it for notes, all right?